Okay, so what we learned yesterday was how to identify the forces that are acting on an object, right? So you basically look for things that are touching it, and then you have gravity. Simple enough? All right, so let's practice that real quick. Here we go. Here's three scenarios. I want the FBDs of all three of those. Go. I drew a little dotted red boundary to kind of help you visualize, like you're isolating the object and you're trying to see what's touching it, right?
The second one is the car like driving, or is it like
No, it's just coasting
just coasting?
across there. Yep. And you sort of see, right? There's no friction, right? Because that's the frozen lake implies ice, no friction. It was the implication of that. And then I sort of drew motion lines on there, right? So you see it's definitely moving to the right. Let me make sure this is on a pen. Yes, this is on the pen. Can I call on some people around to kind of go up and do some of these answers? Henry, you look like you're done. You want to do the first one?
Sure. How do I do it?
Yeah, you just touch screen. It's a little bit weird to use that first if you haven't touch screen. Sick. Um, Carter, have you done the second one?
Yeah.
Yeah, why don't you, could you put it up there? So that first one, normal force and gravity. Okay. Because nothing else is touching it. All right. Oh, that one. Let's see. Is anything else touching it besides the road? So there wouldn't be any other arrows, right? Besides gravity. So I mean, in other words, I'm trying to say that I think that looks pretty good, right? There's nothing else touching it. Once again, don't get distracted by the fact it's moving to the right. That's irrelevant, right? We're only looking at things that are touching it. Right? All right, Hayden, could you do the last one? Appreciate it. Is it weird using a touchscreen? Like,
A little bit.
yeah, it's a little. I think I get used to the. There's like a slight lag, but I kind of totally got used to it actually. But oh, he said there's a rope tension. Is what he did. Oh, because there's clearly a rope touching that car. Apparently, he said there's friction. Okay, is it pretty obvious there has to be a rope force for it? because you literally see a rope touching it. But once again, how did Hayden know that there had to be friction in the fourth one? Right, Elliot, what are you thinking?
Well, there has to be friction because if there's only one force going like left, right, force, if there's nothing balancing out, it would be speeding up to the right, but it's going to balance the speed.
Yeah, so if he left off that friction arrow, then that would mean accelerating to the right. But that's clearly not what's happening here. It's going to constant speed, right? So knowing this means there's a balanced force, which means, bam, that's got to be there. And the only thing that could be is from friction, because the road is the only other thing touching it, right? Questions at all? Nice, nice, nice. Okay. Let's do once again a hill problem. Hill problem. Like I said, you're going to see lots of hill problems, so I want to make sure this gets locked in. Take a look at my little tips, though. All right, and I highly recommend you follow them. I would highly recommend you first draw a dotted line that represents the hill. Like I'm going to draw it in green, like a dotted line that represents the hill. Well, I'll draw it in red, I guess. Apparently, that's the color that it chose for me. All right, a dotted line. Okay. And then what that does, it gives you like a guideline for where you put your arrows. So it's just meant to help you kind of visually see what's going on. You'll see it'll be very, very helpful, all right, to have that there. It just makes drawing things easier. Do you see that second tip about not drawing things at 45 degrees? So do you see what I mean by here? See how my hill's tilted? Like what I mean comparatively, a lot of people like to draw their hills like that. Do you see how that's like at 45 degrees? Okay. Now, there's nothing officially wrong with that, so this is more of a tip. Do you see how I drew mine a lot less than 45 degrees? I'm going to recommend you never draw things at 45 degrees. The reasons why right now are not obvious. Okay, they're not obvious. That'll be very helpful later. So I might as well get you in the habit of not drawing things at 45 degrees. So do you see my hill is just a very kind of just sort of a little bit of a tilt. Right? And this will make things pay its dividends a lot in the future. So if you did draw your hill like relatively steep like that, I would recommend you erase it and kind of flatten it out a little bit. Okay. All right. Okay. So then now when you have your hill like this, then you can go ahead and draw your FBD on that. So I'm going to start again. Once again, I'm going to put that was an eraser. I'm going to put my object right there, and then I can go ahead and draw my arrows on that. So the first thing you should have is gravity. Check with me. Is your gravity straight down? Like straight down, right? Not like that, right? Not like this. That's not straight down. I mean straight down, right? So you have to check that. Next, I see the ramp touching it, the hill touching it. That's a flat surface. Flat surfaces can have a normal force perpendicular to the hill. So that's another reason now why you have that red dotted line graph there. You can have a nice normal force that is perpendicular to that red dotted line like that. Ooh, that's a little curvy. I'm not sure why. Okay, whatever. You see that's kind of perpendicular to the hill? Tilted though? There does have to be friction. If there wasn't friction, for example, what would happen to that block? It'd accelerate down the hill, right? Hopefully you guys know that when you stand on an icy hill, you accelerate down the hill. It's like kind of sketchy. But, so in order for that block to be sitting there, it has to be friction. So when you add that friction arrow, knowing that it's to be parallel to the hill, hopefully you know then where friction is in relation to that red dotted line, right? Well, if it's parallel to the hill, has to be exactly along that line, right? So, but then your only choice is either downhill or uphill. Is that pretty clear? But it's got to be along that line. And in this case, just with your intuition. Knowing that that block wants to slide downhill, which direction do you think friction is? What direction? Uphill, right? So it's going to be the uphill one. Now, once again, friction is going to be parallel to the hill, so this means it's going to be directly along that red line. Do you kind of see now how that red dotted line is kind of like almost a guide that helps you kind of draw things kind of the way you want? So that's why that red dotted line this tip is actually really quite nice to have. All right, so friction, and there you go. Okay. Questions at all about these whole problems? All right, what we're going to learn about today is then how you can draw what I call accurate FBDs. What I mean by accurate is that like it really reflects Newton's first law. What was Newton's first law? Newton's first law was to have your FBD balanced if appropriate or unbalanced if appropriate. Right? Unbalanced if it's accelerating, balanced if it's not accelerating. So how about this? We'll start off with a relatively simple scenario right here. You're lifting a pail of water. So let me show you, like, right here. Here's a pail. It's just a bucket on a string, basically, right? So what I want you to do right now is if you could draw an FBD of this bucket. Right? FBD of this bucket. So just imagine, like, okay, well, you obviously have the gravity. I think you're looking at what's touching this bucket, right? Yeah.
So there's two strings pulling.
Let's not worry about the. Don't worry about the two strings. Don't get distracted by that. Yeah, they want to. Just imagine there's a string. So imagine maybe there's a handle with a string on it. How about that? Okay. So yeah, I don't want to make this too complicated. Here I can simplify where this is not a bucket, but it's just a ball on a string like that. How about that? Same thing. Okay. All right. So how many arrows do you have on your FBD? Gravity and tension for the string, right? Simple. And of course, if the string is up, the tension should be up. Let me see if I have more room there. No, let me. Okay. So gravity down, tension up. You could call that force from rope too. I'd be fine with that as opposed to tension. Okay. This is what I would call a rough FBD, which is totally fine actually. There might be times in the future where I might ask to do an accurate FBD, but that's what we're going to learn right now. Accurate FBD, you're a little bit more conscious about the lengths of those arrows and the relative strengths. So for example, all right, here are two different possible motions of that object. So I could be lifting this pail of water, but I could be lifting it at a constant speed, or I could be lifting it up while speeding up. So those are kind of two different things. And what you need to do then is be able to make this FBD accurate with its lengths to represent these two motions, right? So I'll do this one, like for example. Okay, when it's moving at a constant speed, well then hopefully in your brain that means, well, these two lengths need to be the same, right? Because it's balanced. So this FBD would be, now it sort of looks similar to what I have up there already, but I'm going to just try to be a little bit more conscious about making these two exactly the same size. Okay, for that first one. Whereas for the second one, okay, so it's moving up and speeding up, you should be thinking, well, moving up and speeding up has an acceleration that's up. All right, let me pause it there, make sure you guys all remember that, right? Because speeding up means same direction. Well, what does that mean about the FBD? That means the FBD has to be unbalanced, right? Unbalanced in which direction? Up. So you need to adjust the lengths of these arrows to make true that acceleration is up, which means that tension force needs to be bigger than it used to be. It needs to be bigger than gravity. And that second one is an accurate FBD. Right? So do you see what I mean? That first one we drew at the top here is just a rough FBD for that pail. And then the bottom two are accurate FBDs that accurately represent the motion / acceleration of what's actually happening. Okay. Now, some people in the bottom one, the second bottom one, might be tempted, oh, if I know the acceleration's up, that means I have to add another upward arrow. No, you can't add any of the arrows. You already decided already with your rough FBD how many arrows there are. There's no more. There's nothing else touching it, right? So you don't just unbalance it by adding another arrow. You unbalance things or balance things by adjusting the lengths. That's what I mean by making accurate FBD. Is just meaning make the lengths of those arrows truly represent the acceleration that's actually happening. All right. Balanced in the first one, unbalanced in the second one, right? All right, so why don't we try this on try an example for yourself. Okay, here's a scenario right here. So you are standing in an elevator. It's moving up at a constant speed. Draw an accurate FBD of the forces acting on you. So that's a picture of you in an elevator, right? And notice I want an FBD of you. So do you see I drew a little boundary around you so that you can focus on what's touching you. Is that pretty clear? Notice what I didn't draw a circle around. I didn't draw a circle around the elevator. Right? I drew a boundary around you because we're analyzing you. Okay? So I'm assuming you have gravity. Right? And the next thing you're thinking of is, well, what is touching you? What is touching you? The floor of the elevator. The floor being a flat surface, right? Which means flat surfaces can apply a normal force, correct? In which direction is that normal force? Perpendicular to the flat surface, the floor, which happens to be what you guys just said was up, right? Anything else touching you? Anything? Nope, then you're done. How many arrows then in total? Okay, and then if you want to make it accurate, what has to be true about those two forces? Yeah, Drew. Okay, you say that normal force has to be a longer line than gravity. Do you guys all agree with that? Why would you say it has to be longer? Because you're moving up. What do you guys think about that statement? Yeah, Knox.
Well, I would say that I said it's a constant speed.
It says it's moving at a constant speed, right? What do you guys think about that? What does that mean? So what has to be true about these two forces then? Okay. So in other words, is the moving up important? No, that was a distractor, right? As soon as you see the constant speed, it needs to be balanced, right? Is that pretty clear now? Do you see that thinking process that hopefully was going through your head? Like, yeah, if you saw them moving up a constant speed, what? Balance forces. Are we okay with that? So be super careful about that. Really pay attention to those words, constant speed. All right, good? So any questions about the fact they needed to be balanced? Bam, balanced, right? So how about this? Let's make some other modifications. Oh, yeah, by the way, let me clarify something. Notice I told you that the elevator is moving up at a constant speed, but some people kind of get distracted. Oh, well, you're not moving. Well, you are moving. If the elevator is moving, then you are doing the exact same thing with the elevator is, right? Because you're in the elevator, right? So if I say the elevator is doing something, that you are doing this exact same thing as the passenger. Okay. So how about this? Let's keep on going over the variation of this. Okay. Well, what if the elevator was doing different things? How would your FBD change for these two scenarios? That's what I want you guys to do then. All right? So, like, for example, what if the elevator was moving down and speeding up? Or what if it was moving down and slowing down? Like, that would be, say, you're on the top floor. And you get in the elevator and you push the ground floor. And then, so obviously, it's going to start moving down and speeding up, right? Or then what happens if you reach the bottom floor and you're going to slow down at the bottom, right? You're moving down, slow down. So those would be those two scenarios, right? So what would change about your FBD? That's kind of what I wanted to know. So on the side here, I'm going to draw what you did before in the past, right? In the previous one, here, actually, I'm going to shorten it. Okay, the previous one, gravity and normal force were even. That's if you're constant speed, right? So now what would change about that FBD for these other guys, right? So for this moving down, speeding up scenario, what is going to be different about that? Dude, why am I literally pulling the exact same names as before? Uh, Holy damn. Can I get somebody who's actually here? Joseph, what do you think? So you want to parse this down right here. Moving down, speeding up. First thing you want to think about what direction that acceleration is. It's moving down and speeding up. What's the direction of acceleration? Down, you said? Down. So everybody agree that moving down and speeding up means acceleration is down? So what has to change about your FBD? It needs to be unbalanced down, right?
Yeah.
So what's got to be true about these forces? Okay, did you guys hear what he said? The gravity force has to be bigger than the normal force? I'm actually going to make a slight variation to what he said. Instead of saying gravity is longer than normal, I'm going to say that the normal force is shorter than gravity. Sort of the same thing. The subtle point I want to make with that is that gravity never changes. In all of these three scenarios, gravity is the same length. Right? So I'm going to put gravity in this last one too. Gravity is the same length for all of those. And it's the normal force that changes out of all three. Do you see the kind of subtle difference I mean? So you don't really make gravity longer. You should actually make normal force shorter. Do you see the kind of subtle difference in that? I mean, not what Joseph said isn't necessarily wrong. I'm just going to make a subtle change to what he said. Okay, so do you see that normal force has shrunk? I'm going to tell you later what affects the gravity. Basically, the gravity is a function of like how heavy you are. Right? And obviously, you're not changing weight magically unless you like eat more food, have fire, and another. That'd be pretty weird. But okay, so that gravity error is always going to be the same size. Okay. Questions all about this middle one? So then this last one, then. What's going on with that last one? Elliot, last one.
The last one, we want to have the normal force be longer than the gravity.
So there, the normal force is going to be longer than gravity because that's an acceleration that's up, right? Because moving down, slowing down is an upward acceleration. So you see the difference between those three FBDs is just the size of the normal force. In the first one, normal force is equal to gravity. In the second one, normal force is less than gravity. In the last one, normal force is greater than gravity, right? Just to get the correct acceleration you need. In the first case, no acceleration. Downward acceleration, then upward acceleration as you go along, right? I want to take a little side note right here. If you've ever been in an elevator, you may notice that there's sometimes you feel heavy, and sometimes you feel light, and sometimes you just feel like it's like regular. That's this normal force. Normal force is your brain sensation of weight. So when your body interprets as weight is the normal force. So see like right here, the first one, when you're just standing right here, you feel like regular weight. But you see in the second one, say that normal force is less than your weight, you're going to feel lighter as a result. Your body feels lighter. And in that third one, your body would feel heavier. So oftentimes if you're in elevators, you feel this change in weight. So like, for example, like how about this? You don't really feel it in the east elevators because the east elevators, the acceleration, the accelerations are pretty small. So these differences are pretty minor. So you may not feel it. But if you were to ever go in an elevator in a taller building, like maybe like one of the taller hotels downtown, or actually one elevator that's pretty nice is in the Wells Fargo building. Do you know the Wells Fargo building? Like it's the taller one near the top. So if you ever go in there and somehow get into those elevators, not the easy elevators to get into. Why? Because it's protected by security guards. But if you're somehow able to sneak past the security guards, or like beat up the security guard, say, dark city, or whatever. Get past the security guards, get into those elevators. Those elevators, they will speed up and slow down pretty significantly. And when they speed up or slow down, you'll get FBDs that are like this or this, which means when the normal force is bigger than gravity, you're going to feel heavy. And you feel it. Like, whoa, you feel heavy. And the top, maybe, or not at the top, when it's, when your normal force is less in gravity, you might actually feel lighter. And then, but notice in the middle of the travel, when things go at a constant speed, you'll just feel like you don't even know you're moving. You're just in there like, what, is this elevator even moving? Right? Because you feel just like like if we're just standing still right here, because you feel normal weight, right? But so this, if you ever get into an elevator and you sort of, hopefully next time you get an elevator now, maybe you'll think about, you'll sort of recognize the sensations of like, oh, I feel heavy or I feel light. Well, this is what's going on here, okay, from physics point of view. Okay, so think about that next time you're in an elevator. Okay, moving along then. Here we go. Oh, by the way, when you're drawing these accurate FBDs, here's where having like even graph paper notebook is kind of nice, because then you could actually use the grid of the graph paper to kind of judge lengths of things. I mean, you can do it with lined paper too, especially with the horizontal lines, because then you can use the vertical spacing of those lines to kind of gauge the length of an arrow and stuff like that. Okay. But, okay, why don't you go ahead and draw a rough FBD of this wagon. A rough FBD of this wagon. So think of all the things that are touching that wagon. Notice the subtleties though. Do you see where I drew the boundary around? I drew a boundary around the wagon. Not the girl with the wagon, just the wagon itself. Oh, and there might be one thing about this that I forgot I might need to talk to you about. But why don't you just go ahead and get started? And just to simplify things, I got rid of friction, right? So there's no friction on there. So you should have gravity, correct? You guys got gravity on there? I'm going to draw this over on this side right here. We got ourselves some gravity action, right? Clearly looks like a rope touching that sucker. Clear as day. So you got your rope force. Shabam. You clearly have the ground touching it, right? Perpendicular to the ground is up, normal force. The ground could have friction too, which if there was friction, it'd probably be backwards to the left, except that I told you to ignore friction, right? So don't have the friction error. Now, there's another force that oftentimes people miss. Do you see there's a girl touching it? So you would need the force from the girl, all right? Now, the force from the girl would probably be pushing down on that wagon. Do you see? Because the girl's sitting on top of the wagon. Now, I didn't talk about this before, so let me make a little aside. What happens if you have more than one force in the same direction? If you have multiple arrows in the same direction, you just kind of stack them like that. You see side by side? So like, do you see this blue one is a super extreme example. You could have FBDs with like 3 leftward forces or 2 upward forces and 3 downwards forces, something like that. Those would be kind of extreme. You don't see this very often, but you could. Right? So that's how you draw multiple forces. Fair enough? Okay, so in this case, let me go back to the one we were at. All right, so this is the first one we've had where we've had multiple arrows down. So do you see there would be another downward arrow? And once again, you label that with the name of the object that's touching it. So that would be force of girl, correct? Because it's the girl that's touching the wagon. So you just write force of girl. Okay. We're good to go? Okay, now this is not accurate. That's a rough FBD, by the way. So now our job is to make it accurate. Now, first things first is that you want to look at horizontal separately from vertical. So you see a horizontal? You see only one horizontal force? This clearly means that wagon is guaranteed to accelerate to the right. Is there any question how I know, just look at the FBD, that wagon is guaranteed to accelerate to the right? Because it's clearly unbalanced to the right, correct? But we need to know what's going on vertically. So here you need to kind of use some like knowledge of the situation. When you pull this wagon, is the wagon going to be moving vertically at all? Is it? If not, then what has to be true about those vertical forces? Right? Are you guys actually answering me, please, when I ask a question? Once again, what is true about the wagon vertically? Okay, why once again? Why do the forces have to be balanced vertically? Yeah, because it's not even moving vertically at all. Is that pretty clear? So we need to make this better. I'm going to throw in my little grid right here. And so this, I'm going to make my dot, and I'm going to make my gravity arrow say 4 units big. You see it's 4 units big right there? I'm going to go ahead and put this tension arrow. That the horizontal is kind of irrelevant because that thing's by itself. Okay. But then if I have another girl arrow right here, now I'm going to tell you right now, you don't really know the size of that girl arrow compared to the gravity arrow. It could be 1, 2, 3, 4, 5, 8. Like you don't really know. I'm just going to randomly make it 3 big. All right. Oops. That's more than 3. I'm going to make it 3 units big right there. All right. Well, if that girl arrow is 3 units big and that gravity arrow is 4 units big, you should know exactly how big to make that normal force arrow, right? Exactly how big should my normal force arrow be? How big again?
4.
Well, hold on. It's not moving vertically, right? So do you see right now, this original one is not balanced. Why? Because if those 2 downward arrows are way bigger than the 1 normal force arrow. I mean, together, combined. See what's going on there? So if I put these 2, the size of both those, and I stack, like add them together, I would clearly get normal force is not big enough to be balanced, right? So do you see, as originally drawn, there is way too much down compared to up? Is there any question about what you're seeing there? So I maybe should have started with that. So how about this? When I go back to this one right here, do you see where some people are saying that the normal force needs to be 7 up? Where did they get the 7 from? The 2 forces added together, right? So if the girl one is 3 and the gravity one is 4, now how big is normal force? Is it pretty clear that the normal force should be 7? 1, 2, 3, 4, 5, 6, 7. So you should have an extra big normal force in order for this to be balanced vertically. You see where we're going with that here? Now, what if the girl and gravity were both 4? How big would the normal force be? And then if the girl happened to be 5 and the gravity is 4, then the normal force would be 9, stuff like that, right? So right now you don't know how big the girl and the normal force are. The girl and the gravity are compared to each other. I just kind of made those 2 up. But if you know the size of those 2 downward arrows, there is no guess what the size of the upward arrow is. Is that pretty clear? Now are we all good with that? Okay. So in other words, if the girl were heavier, so like that big, then I would have to make the normal force even bigger to accommodate for that. Now it's 5 plus 4, 9. Okay? Questions at all about this? Okay. So let's try another scenario. Here, let me just demonstrate it right here. There is a book on this table, and I'm trying to lift it up, so I'm lifting it up, but it doesn't move. Not because I'm not strong enough. Trust me, not an issue. All right? Strength, never an issue for guns like this. All right? So, purely for demonstration purposes, I assure you, I'm going to be lifting up on this book, and it doesn't move. All right? So, lifting up on this book, and it doesn't move. FBD. Accurate. So to make this accurate, I'm going to enlist the help of my little handy dandy grid. So I can have some nuts to go with. And like I said, you can use the lines on your sheet of paper to try to make things accurate with some lengths. So just to have things consistent with me, I'm going to just make my gravity arrow, say, I don't know, 5 units big. Okay, what other forces should there be on your FBD? The normal force from the table, right? And then, what else is touching that object?
Your head.
hand. So you have a force of hand pulling up in that sucker, right? Now, of course, if you were to make this accurate, what has to be true about those two upward arrows? Now, how about this? What if I drew it like that? Is that okay? No, definitely not accurate right there, because it clearly looks like if you have 5 and 5 up, that's a total of 10 up and 5 down. That's not balanced, right? Yeah, what do you think, Drew?
The two upward-facing lines have to be 2.5 units if you're
Okay, he's saying both upward arrows would have to be 2.5. Do they both have to be 2.5? What were you saying, Avery? They just have to total 5. It doesn't have to be 2.5. It can be 2 and 3. It can be 1 and 4. 2.5 and 2.5 if you want. 2.2 and whatever, 2.8. It took me a while to think about that. Okay. So, like, how about this? If I'm only pulling up with 1 unit, then if that's my hand, then how big is normal force? Gotta be 4, right? Everybody clear with that? Or what if I pull a little bit harder? What if I pull with 2? How big is normal force now? Guys, with me? If I pull with 2, how big is normal force? And then notice that what I'm trying to show you here is that normal force is not fixed in size. Right? It can change depending on the scenario. If I pull harder, the normal force will just do whatever it takes to adjust. Right? So as I pull harder, this other arrow goes down to make it just balance out to 5, right? And so, maybe at a certain point, maybe my hand is exactly 4 units big. No, sorry. Maybe my hand is 5 units big. I miscounted. I forgot my gravity was. Okay. So if I pull exactly with 5, 1, 2, 3, 4, 5. If I pull exactly with 5, and the gravity was 5, so I'm pulling exactly with 5. How big is the normal force now? So what that's saying is the table's not doing anything, right? If I pull exactly with 5 and the gravity is 5, that table could disappear, and guess what? That book would still be still, right? Question. What if the gravity is 5, but I pull with 6? How big is the normal force? Okay, yes. A common answer is like, wait, normal force is -1. Except that what these guys are saying, well, if I'm pulling with 6 and gravity is 5, what's going to happen to the book? It's going to accelerate, which means the table's not even touching it anymore, so there not even is a normal force, right? So you won't say the normal force is -1. No, I was sort of like, I was trying to trick you guys. Apparently, I cannot trick you guys. All right. So if this were true, then there's no normal force because it actually accelerates up and off the table. So normal force isn't even a thing anymore. Okay. By the way, I don't want to imply that they have to be like perfect integers, right? In case that wasn't clear. Like it doesn't have to be 2 and 3. It could be what together? 2.5, 2.5, 2.2, 2.8, stuff like that. Okay. It could be any decimal as long as it adds up to 5. All right, good with that? Any questions about this one then? Next, I'm just having a series of examples. Each one is meant to reveal kind of a slightly new wrinkle. All right, here we go. There is me. I'm pushing a file cabinet into a corner, so it's just like right here, this desk. I'm just pushing it into its corner. Why am I pushing it into a corner? I don't know. Just part of my workout once again. How one gets so beastly. If you're wondering how one gets so strong as me, this is part of my workout. This and lifting books off tables. All right. So workout tips from Sue. Go FBD. You're drawing an FBD of the file cabinet, by the way, right? So you're isolating the file cabinet. Clearly, there's me touching it, or you, or person. I don't know how you're going to write that. Right? Force a person, force a me. Something along those lines. Okay. One of the things that's special about this particular scenario, okay, we already have the ones that we are kind of obvious gravity, right? And then there's the person pushing it. So person pushing it. I'm just going to call that me because I don't feel like writing the word person. Okay. Notice there are two flat surfaces, a wall and a floor. So one of the points of this particular example is that there can be more than one normal force, one for each surface. All right. So there's not just like there's just one normal force for a scenario. Every flat surface can have its own normal force. So you can have a normal force from the floor and a normal force from the wall. And you probably want to label them as such. For example, the normal force from the floor is going to be up, right? Because that's perpendicular to the floor. And then the normal force from the wall is going to be perpendicular to the wall, right? Which is in which direction? And do you see how I'm labeling it? Normal force from floor and normal force from wall. So yeah, that's one of the things I do want to talk about with this particular example. Yes, you can have two different normal forces, right? And then the next thing, although you guys probably know this, what should be true about this FBD in terms of the balance or imbalance? I mean, the file cabinet, what's happened to the file cabinet? It's not moving. So obviously that FBD has to be balanced, right? Okay, here's the next thing. To be balanced, it does not necessarily mean that every force has to be equal to each other. You are going to separate horizontal from vertical. This is going to be a consistent theme all year long. So you just have to make sure that the two horizontals cancel each other out. And then separately, the two verticals cancel each other out. They don't have to be the same length as each other, like the diagonal and the vertical and the horizontal. Like, for example, how about this? This can even be like this. You see that? And then like that. That's also completely balanced too. Is that pretty clear? So it doesn't necessarily need to be perfectly four symmetric arrows. As long as the horizontals are balanced, cancel horizontal. Verticals are balanced, cancel vertical. Done. Okay? We good to go with that? So now it'll be completely balanced. All right. So that's the other aspect of this that I want you to sort of kind of see, is that you're sort of training your brain to look at what's happening vertically separately from what's happening horizontally. The two kind of don't really necessarily connect with each other. All right? Questions at all? Next. Damn. Sadistic. All right. So that is me holding that toy car up against the ceiling. Stupid little sucker. All right. So you're holding that toy car up against the ceiling, and so you want an FBD of the toy car as well. Just so it's super clear, so that is a picture of me, because this is what I like to do with little kids. I like to bully them. So see my hand is at an angle there. Don't worry about the angle of my hand. Just pretend I'm pushing straight up. We're going to deal with angled forces later. So just pretend my hand is pushing straight up on that car. All right, we'll just keep it simple. Sure. How many arrows you got on the FBD? I see some people saying 3. Gravity is obviously one of them. Looks like there's clearly a hand touching it, pushing it up, like you said. And then you have a ceiling. What direction is the normal force from the ceiling, by the way? Down, perpendicular to the ceiling, which is straight down. So you have 2 down arrows and 1 upward arrow. And obviously that tow car is not moving, right? So then if you want to make this accurate, which I'm hoping it is, because this is the whole point of this lesson is to learn how to draw accurate FBDs, that you should see the upward arrow should be extra long. Is that pretty clear? The size of the 2 downward arrows relative to each other, that's maybe a little bit variable, but at least the upward arrow, I should at least see an extended upward arrow. Is there any question what I mean by why there should be an extended upward arrow? Because of this balance, you have 2 down, the 1 up has to be longer. Right? So say that's gravity, and that's normal force. Well, then the upward thing. Actually, how about this? Maybe the most accurate way to say it is that the size of the normal force is going to respond to however hard I push it. Like, for example, if I make this longer, then that normal force is going to increase as a result. Right? So let me touch some numbers. Say the gravity was, say, 4 units big, and my hand force was 10 units big. How big is the normal force? Is it clearly 6? But if I were to push with 11, then the normal force would increase to become 7 as a result, right? So once again, here's another thing where the normal force, it can just adjust to whatever it needs to be, right? Good with this one? Next. Dude, you gotta admit, that picture is kind of fire. Look at that, dude. Come on now. Look at those hands. Straight up sick. You can see the knuckles on those. That is awesome, if I do say so myself. All right. That picture is nice. All right, so you're drawing an FBD. By the way, there definitely is friction here, so I want you to make sure you do include friction. Dude, hands all tatted up too. Shut, look at that. That's extreme, dog. I'm not sure if any of you have finger tats. I'm not sure if I would recommend it. I hear it probably hurts a lot. But totally worth it to have love and hate engraved in your skin. All right, I'm going to ask you guys a series of questions that I'm going to ask a lot over the next couple weeks as a way to check to see if your FBD is right, and as a way to sort of, for you to see if you are visualizing your FBD correctly. All right, first thing I'm going to ask, how many total arrows do you have on your FBD in total? I hear a lot of people saying 5. If you only have 4, you might be missing friction, because I told you you need to have friction on your friction from the ground. No, that's 5. Next question. How many vertical arrows do you see? That's vertical meaning both up and down. How many vertical arrows do you have? 3? How many horizontal arrows do you have? 2? Okay, so that's going to be a common set of questions that I'll use kind of to look. As we go to more and more complicated FBDs, I'll ask you, like, how many total arrows do you see? How many vertical arrows? How many horizontal forces? Stuff like that, right? So now let's deal with the balance and imbalance. Is it pretty clear that box is not going to be moving vertically at all? which means those vertical forces need to be balanced. By the way, when you say 3 vertical forces, how many were down? 2 and 1 up? Okay. So if they're going to be balanced, if you have 2 down and 1 up, I'm hoping that your up is extra long. Is that pretty clear? Right. So check yourself. Do you have an extra long up arrow from the normal force? How long? The size of the 2 downward arrows added together, right? All right, next let's look at horizontally. Should the horizontal arrows be balanced? Look. I see you guys shaking your heads. How do you know they should not be balanced? Because it's moving to the right. Wait, is that the only thing that matters? This phrase? Those 2? So which one should be bigger? The rightward one or the leftward one? Because those 2 together mean acceleration to the right, which means horizontally the rightward arrows need to be bigger. Yeah, question. Sure. Yeah. So hopefully, roughly, I'm not going to go over totally because you guys already said you had these arrows, right? You would have 2 downward arrows and an extra long one, right up, and then this one would be longer than that. So along the lines of the general shape. Now, I would say these 2, you don't know how these 2 compare to each other. Okay, but clearly those 2 downs should add up to the up. Fair enough? So now you sort of see how to make accurate FBDs and how to visualize whether things should be balanced or unbalanced. All right, what you guys should do now before you go to this activity, a couple of things I want to talk to you about. First, well, no, go ahead and go to this activity. All right, go ahead and work on that. To go to that, so you need a computer. So go to that computer and go ahead and do that.